Hello, I hope that you are all of you doing well and safe. I'm having the pleasure to give a presentation entitled Study of the Sensitivity of GTN Parameters during the first Virtual European Conference on Fracture. Before dealing with my presentation, let me give you the contents that I will work on today. I'm going to start by general introduction, then I'm going to give you a brief introduction about my Gaussian model, then results and interpretation, then conclusion and my future plan. Oh, before dealing with the calculations and the simulation, etc., let me just tell you one important thing, that this work is taking up part of a big European project called Atlas Plus, dealing with the nuclear safety of reactors from generation 2 and 3, that we have to ensure that they are going to work properly for at least few decades, which means that we need to ensure that all the parts are going to work properly. And the pipes are a very important part in the nuclear plant. Well, I guess you are shocked because of these pictures. All of you, they are pictures of catastrophes. But I guess as you are experts in the field of fracture mechanics, you know that the main reason behind this accidents is the presence of cracks. Yes, the presence of cracks in the material is very dangerous, and we need to study how they are initiated, how they propagate, and we need to predict the failure of material in case of the presence of crack. Then we can avoid catastrophes. So maybe now the question, how we could predict the failure based on local approach. Yes, so there is various models that are based on local approach that we can use to predict the failure of material. And one of the materials that I'm working on is the pipeline. But still, we need to find a way that we can predict the failure by the cheapest way. As you know, if we want to make experiments on a pipeline, it will take a lot of money and also special equipments for such kind of tests. So we have to find a way that we can predict the failure of pipe, but in the cheapest way, and the results that we have to find, they have to be correct. So this is the cheapest way. The cheapest way is starting from small scale specimen to the large scale in reality, for example, pipelines. So how we can start, for example, from CT or from SENT specimen, then we can predict the failure of pipelines. Yes, I mentioned that there are various models that they are based on local approach. Well, I decided to use Gaussian model because it shows that it's a very strong model that scientists and researchers and also it's used in the industry. Well, it's not Gaussian model, it's GTN model. But Gaussian was the first person who found or who developed the model. But there was two scientists they called Tvigard and Nedelman. They could develop the model, then we can use it in the real in our industry or in our applications. So to summarize, I would like to mention that our GTN model came here to simulate how the ductile failure happened in the steel. And as you can see here, this is a picture to show the failure in case of steel, and this is the coalescence phenomena in case of ductile failure. So our two scientists, Mr. Twigger and Mr. Needleman, they came and they tried to add the microvode coalescence, which was not present when Gerson made his first model. Okay, so before or without dealing with the details of such kind of complicated equation, I would like to mention or to tell you the most important thing. The most important thing is we need to determine those 8 parameters. Then we will be able to predict the failure of a huge component from small scale specimen. Luckily, the values of Q1 and Q2, according to the literature and to our previous scientists and researchers, they could find that Q1 and Q2 are constant. So I'm going to focus on the rest, which are 6 parameters. Now we have 2 questions: how we could determine these parameters, and how those parameters are sensitive. Which are the most sensitive parameters that could influence our results? So I just mentioned that the values of Q1 and Q2 are fixed, and as you can see in the table, they are quite fixed, and we can take Q1 as a 1.5 and Q2 the value of 1. Still, the other values of the other parameters, they vary, which means that we need to study the most sensitive parameter of those 6 parameters. So how we could determine these parameters? I'm not going to go deeply in this topic because this is not the purpose of today, but I would like to mention that the most known method is the direct way, which is the combination between the experimental and finite element results. But after the development of technology and computer science and artificial neural network, we could combine the direct method with others, for example with the artificial neural network or with hyperparticle swarm optimization. Then we can find those parameters in less time, because in the direct method it will take a lot of time, but if we combine it with other methods, such kind of artificial neural network, which I have done in my work, yes, to be honest, it reduces a lot of time. So what we have found after using the direct method and the artificial neural network, that we have different combination of 8 parameters, but the same results. How? So macroscopically, when we simulate the experiment, yes, we find that our finite element results, yes, predicts very well the experimental results. But if we see the parameters, yes, they are quite different, which means that the voids, how they behave microscopically, is different. So we need to find what are the most sensitive parameter, why we have this, why we have different kind of combination but with the same result. So I decided to study or to determine the most sensitive parameter, and that was done by using different geometries and different specimen. So I use our NT specimen and CT specimen. So as you can see in the picture, 240 simulations with different set of parameters. I will explain. So 240 simulation, which means for each specimen I have done 120 simulations. Why 120 simulations? Because 120 over 6, which are the 6 parameters, is 20 simulation. So for each simulation I have done for each parameter I have done 20 simulations. So I fix one parameter, then I did 20 simulations with I fix 5 parameters, then I have done 20 simulations with different numbers of that variable. Then I did the same with the others. So I hope now it's clear. So we fix 5 parameters, then we took one parameter and we did the variation of this parameter, then we did the rest with the others, and that's what I have found. So that's by our NT. So now our NT specimen, we will see what are the most sensitive parameters, which means when we have done few changes in this parameter, how this influence our results if let's say that the other parameters are fixed. And this is what I find. I find that there is slight change when we vary the value of f0, which are the variation of which is the initial void volume. So, but still, to be honest, it's not very large. The variation is not very big, but still, that when we try to, it affects our results. But I will show you later the most sensitive parameter, which is the time of voice nucleation, epsilon n. Yes. So as you can see in this picture, by doing small change in this parameter, we find that it's really affect the results. So we have to pay more attention to this parameter. Then I did change the geometry. I took the CT specimen. I have done the same thing, 120 simulation, 20 simulations for each parameter of the 6 parameters that I told you. Then let's see when we change the geometry if we will find the same parameters or not. And this is what we have found. We have a new parameter which is called the void nucleation mean quantity, which is Sn. So as you can see here, small change in this parameter influence our results. And we have another parameter which is called Fc. Small change in this parameter also influence our results. So as you can see, when we change the geometry, new parameters appear which they are also very sensitive to small changes. Then as we find in case of CT, we have the same parameter which is the strain at the time of void nucleation, which is the most sensitive parameter in both cases, in case of NT and in case of CT. So let's summarize what we have found. We have found that we have different cases of the most sensitive parameter, epsilon and f0 and fn, etc. But which means that in order to find the right combination of the Gaussian parameter that we can use in order to predict the failure, it's not an easy task. We have to pay more attention to the values of those parameters. They have to be logical. They should have a physical meaning. They should not just to be random parameters. And we have to know that when we change the geometry, the sensitivity change, and we need to pay more attention to the value or to the expression, to the parameters that I found in my study. Because they are small change in this parameter, just influence our results in a big way, as you can see. Well, maybe you are asking, I mentioned 6 parameters and now I'm showing just 3 parameters. Why? Well, to be honest, I would like to tell you that for the other parameters, I have done 20 simulations for each of them and there was no influence when I made the small changes. So I find that there was a same curve and slight, very small change. So I decided to put in my presentation today just the most sensitive parameter. So in our conclusion, I just would like to mention that uh, the geometries, with different geometries, we have different most sensitive parameters. And I already mentioned that for FF, F0 and Fn, the effect of changes is not very big, which I already mentioned. And the most sensitive parameters for the both geometries for CT and for NT are Sn, Fc, and epsilon n. In my next future plan, I'm going to determine the GTN parameters for pipeline, which I will take in consideration the most sensitive parameter. I will use the artificial neural network, which is the ongoing process. Then I'm going to use the genetic optimization algorithm to determine the Gaussian parameters. That's all for today. Thank you so much and stay safe. Thank you.